Fraunhofer Institute in Germany is revolutionizing the heat pump systems. They introduced a game-changing system that reaches a scope value of up to 9. This means nearly twice as efficient as the heat pumps currently available on the market.
A heat pump that can cut heating costs by up to 90%. That's twice as efficient as anything currently on the market, small enough to fit in a closet, completely silent, and works even in poorly insulated old buildings. This isn't science fiction. It's real technology being developed right now by Germany's Fraunhofer Institute, and it works without refrigerant. The secret? A strange metal alloy that remembers its shape. But here's the question everyone wants answered. When can you actually buy one? Why traditional heat pumps have hit their efficiency ceiling? Every heat pump on the market today operates on the same basic principle that's been around for over a century. They use refrigerant, a special liquid with an extremely low boiling point, typically below -20 degrees Celsius. This means even on the coldest winter days, the outdoor temperature is warm enough to make the refrigerant evaporate. When it changes from liquid to gas, it absorbs energy from the outside air. That's the clever part. A compressor then squeezes this gas, which makes it hot, and this heat gets transferred to your home's heating system through a condenser. After releasing the heat, the refrigerant cools down, becomes liquid again, and the cycle repeats. This refrigeration cycle is everywhere. Your fridge uses it. Air conditioners use it. Heat pumps use it. For decades, engineers assumed this was simply the best and perhaps only practical way to move heat efficiently, and they've been optimizing it relentlessly. Modern heat pumps are engineering marvels compared to systems from 20 years ago. But here's the problem. They've basically hit a wall. The laws of thermodynamics impose hard limits on how efficient this process can be based on something called the Carnot cycle. Current refrigerant-based heat pumps can only achieve about 64% of the theoretical maximum efficiency. That's actually impressive, but it means there's a ceiling. No matter how much engineers tweak the design, add better compressors, or find superior refrigerants, they can't push much beyond this barrier. The technology is fundamentally limited by the physics of phase change and compression. Plus, refrigerants themselves are becoming a problem. Many are potent greenhouse gases, and regulations keep tightening. The industry needs something different. The material that changes everything. Understanding nitinol. That something different might be sitting in a lab right now, looking like an ordinary piece of wire. Nitinol is a nickel-titanium alloy, and it has a superpower that seems almost magical. You can bend it, twist it, crumple it up into any shape you want, but heat it up and it springs back to its original form like it has a memory. This isn't a trick. It's a fundamental property of the material's crystal structure. Nitinol exists in two different phases. When it's cold, it's in what scientists call the martensite phase. The atomic structure is loose and flexible, which means you can deform it easily. But when you heat it up, the atoms rearrange themselves into a different configuration called austenite. This structure is rigid and stable. The atoms essentially remember where they're supposed to be, and they pull the material back into its original shape. This phenomenon is called the shape memory effect, and it's been known since the 1960s. What makes this relevant for heat pumps is what happens during this transformation. Energy doesn't just disappear. When you heat up nitinol and it changes shape, it's converting thermal energy into mechanical work. The material is literally doing physical work as it moves. And here's the reverse. If you apply force to deform the material, it heats up. It's converting mechanical energy into heat. This process is completely reversible. You can cycle it endlessly. Heat it, it moves and absorbs energy. Compress it, it releases heat. Cool it down, it becomes flexible again. Apply force, it heats up. Over and over, thousands or even millions of times. This is what scientists call a caloric material, and it opens up an entirely new way to pump heat. Instead of relying on refrigerant changing from liquid to gas, you use a solid material changing its crystal structure. No compressor needed, no refrigerant needed, no phase change between liquid and gas. Just a solid piece of metal that absorbs and releases heat through mechanical deformation. The Fraunhofer Institute recognized that this property could revolutionize heating and cooling technology. They're not alone. Research groups worldwide are exploring caloric materials, but the German institutes are leading the charge in turning this into practical, commercial products. How caloric heat pumps actually work without refrigerant. So how do you turn a piece of shape memory wire into a functioning heat pump? The concept is surprisingly straightforward, though the engineering is complex. Instead of circulating refrigerant through coils and compressors, a caloric heat pump uses bundles of nitinol wires or plates arranged in a heat exchanger. The material sits between two thermal reservoirs, one connected to the heat source outside your home and one connected to your heating system inside. The cycle starts with the nitinol in its cold, flexible martensite phase. In this state, it's placed in thermal contact with the outside environment. Even cold winter air contains heat energy, and the nitinol absorbs this heat directly. No evaporation required. The material warms up slightly and begins its phase transformation toward austenite. Then comes the mechanical part. The system applies stress to the material, either by compressing it, stretching it, or bending it, depending on the design. This mechanical work forces the crystal structure to complete its transformation, and in the process, the material releases heat. A lot of heat, more than it absorbed from the outside air. This released heat is captured by the indoor heating system's water or air circulation. The hot nitinol has now transferred its energy inside your home. Next, the mechanical stress is released. The material relaxes, and as it does, it cools down below the starting temperature. It's now ready to absorb heat from the outside again, and the cycle repeats. The whole process happens continuously, with different sections of nitinol material at different stages of the cycle, creating a steady flow of heat from outside to inside. What's been eliminated? The entire refrigerant circuit. No compressor to pressurize gas, no condenser coils with toxic or greenhouse warming fluids, no expansion valve, no risk of refrigerant leaks. The system is mechanically simpler in many ways. You still need a mechanism to apply force to the nitinol, but this can be done with electric motors or other actuators that are far quieter and more compact than traditional compressors. The heat exchangers themselves are smaller because the material has excellent thermal properties. And because you're working with solid materials instead of gases and liquids under high pressure, the safety requirements and maintenance concerns are dramatically reduced. The entire unit can be significantly more compact, potentially 30 to 50% smaller than conventional systems, which means it could fit in spaces where traditional heat pumps simply won't work. The numbers that matter, efficiency breakthroughs explained. Here's where things get truly exciting. Remember that 64% of theoretical maximum that conventional heat pumps can achieve? Caloric heat pumps can reach up to 85%. That might not sound like a huge difference, but in practical terms, it's massive. The efficiency of heat pumps is measured by something called SOCOP, which stands for Seasonal Coefficient of Performance. It's basically how many units of heat you get out for every unit of electricity you put in. A good modern heat pump might have a SCOP of 4 or 5. That means for every kilowatt hour of electricity consumed, you get 4 or 5 kilowatt hours of heat. The Fraunhofer caloric heat pump achieves SCOP values between 8 and 10. In some conditions, it can reach up to 9, which means 9 units of heat for every unit of electricity. That's nearly double the efficiency of current technology. Let's put that in real terms. If your annual heating bill with a conventional heat pump is €1,000, the caloric system could potentially cut that to around €5 or even less. Over a decade, that's thousands of euros in savings. Over the lifetime of the system, potentially tens of thousands. But efficiency isn't just about saving money, it's also about capability. Higher efficiency means the system can operate effectively in more challenging conditions. It can handle colder outdoor temperatures without losing performance as dramatically as conventional systems. It can deliver higher indoor temperatures when needed. This is crucial for retrofitting older buildings, which often require higher water temperatures in the radiator systems. A conventional heat pump struggles in these situations because its efficiency drops off sharply as the temperature difference, delta T, increases. The caloric system's superior baseline efficiency means it maintains economic viability even when facing large temperature differences. It's simply so far ahead in efficiency that it compensates for the same thermodynamic challenges that cripple conventional systems. Why this solves the old building problem. Old buildings are the Achilles heel of heat pump adoption across Europe. These structures, built before modern insulation standards existed, leak heat like sieves. They often have single-pane windows, uninsulated walls, drafty doors, and require high-temperature heating systems with radiators that need water at 60 or 70 degrees Celsius to keep rooms warm. For a conventional heat pump, this is a nightmare scenario. The colder it is outside and the hotter the water needs to be inside, the worse the efficiency becomes. In the worst cases, the heat pump consumes so much electricity trying to maintain these high temperatures that it's actually more expensive to run than a gas boiler. This is why energy consultants usually tell owners of old buildings that heat pumps aren't economical without extensive renovation first. You need new windows, wall insulation, upgraded heating systems with underfloor heating or larger radiators. The costs can be staggering, often exceeding the cost of the heat pump itself. Many people simply can't afford it, which is why old buildings remain stuck with fossil fuel heating. The caloric heat pump changes this calculation because it operates at such high baseline efficiency. Even when faced with large temperature differences, it remains economical. It can deliver the high temperatures these old systems need without the electricity costs spiraling out of control. For homeowners with poorly insulated buildings consuming over 100 kilowatt hours per square meter per year, this technology could finally make the switch from oil or gas heating financially viable without requiring a complete building renovation. It doesn't mean insulation becomes unnecessary. Better insulation is always beneficial and will save energy with any heating system. But it means the heat pump itself becomes a realistic option even before that renovation happens, removing a major barrier to adoption. Size, noise, and cost. The practical advantages. Beyond efficiency, caloric heat pumps offer practical benefits that matter in daily life. First, size. Eliminating the bulky compressor and complex refrigerant circuits means the entire unit can shrink by 30 to 50%. This matters more than you might think. Many homes, especially in urban areas, simply don't have space for large outdoor units. Apartment buildings face even bigger challenges. A compact caloric heat pump could fit in utility closets, small balconies, or basement spaces where conventional units won't work. Then there's noise. Traditional heat pump compressors are loud, they cycling on and off, the vibration, the whooshing of refrigerant. It's annoying for homeowners and their neighbors. Some municipalities have noise regulations that effectively ban outdoor heat pump installations in dense residential areas. Caloric systems, using gentle mechanical actuation instead of high-pressure compression, are nearly silent. This alone could accelerate adoption in noise-sensitive environments. Cost is the other critical factor. The materials themselves, primarily nickel and titanium, aren't exotic or expensive in small quantities. The manufacturing process is more straightforward because there are fewer components. The Fraunhofer Institute estimates production costs could be at least 30% lower than conventional systems. Lower upfront cost combined with dramatically lower operating costs makes the economics compelling for nearly everyone. Add in reduced maintenance costs because there's no refrigerant to leak or compressor to fail, and the total cost of ownership drops even further. These practical advantages mean the technology isn't just for enthusiasts or wealthy early adopters. It could become the default choice. The reality check, timeline, and market availability. Now for the question everyone actually wants answered: when can you buy one? The honest answer is not yet, and probably not for a few more years. The technology is real, the prototypes work, the physics is sound, but moving from laboratory demonstration to mass production is a long, expensive process. The Fraunhofer Institute and other research groups are currently in the development and testing phase. They need to prove the systems can run reliably for thousands of hours under real-world conditions. They need to optimize manufacturing processes. They need to work with industrial partners who can scale up production. Current projections suggest commercial availability in approximately 4 to 8 years. That's a wide range, and it could shift based on funding, regulatory approvals, and market conditions. Some pilot projects and early commercial installations might happen sooner, probably in 4 to 5 years, but mass market availability, where you can order one online or through local installers, is more likely in the 6 to 8 year timeframe. China and other countries are also developing similar technology, which could accelerate the timeline through competition or complicate it through patent disputes and market fragmentation. What's clear is that This isn't vaporware. Major research institutions across multiple countries are investing heavily. The European Union is funding development as part of its climate goals. Private companies are taking notice. But product development takes time, especially for something as critical as home heating systems, which need to be absolutely reliable and safe. You can't rush that. The wait is frustrating, but it's also necessary to ensure the systems that eventually reach the market actually deliver on the promises. Should you wait or buy a heat pump now? So what should you do if you need a new heating system today? Should you wait for the miraculous caloric technology or go ahead with conventional options? The answer depends entirely on your specific situation. If you have a relatively modern, well-insulated home built after 2000 with reasonable energy consumption, don't wait. A conventional heat pump will start saving you money immediately. Over the next 5 to 8 years before caloric systems become available, you'll accumulate substantial savings compared to continuing with oil or gas. The benefits of waiting simply don't outweigh the benefits of switching now. However, if you own an old, poorly insulated building where current heat pumps aren't economical, the calculus is different. A conventional heat pump installed now might not save you much, or could even cost more to operate than your existing system. In this case, waiting makes sense, but not just waiting. Use the next several years to improve insulation, upgrade windows, add wall insulation, improve the roof. These improvements are economically beneficial regardless of what heating system you have. They'll pay for themselves through reduced energy consumption, whether you're burning gas or running a heat pump. And crucially, by the time you've completed these renovations, caloric heat pumps should be hitting the market. You'll be perfectly positioned to install cutting-edge technology in a properly prepared building. For everyone else in between, it's a judgment call. If your current system is failing and needs replacement urgently, you probably can't wait. But if you have a few years of life left in your existing boiler and your building is poorly suited for current heat pumps, keeping that system running while monitoring caloric heat pump development might be the smart move. The key is to stay informed and flexible. The era of refrigerant-based heating is coming to an end, not because of regulation alone, but because better technology is finally arriving. Shape memory alloys were discovered decades ago, but it's taken until now for engineers to figure out how to turn them into practical heating systems. When they arrive, they won't just be incrementally better. They'll be transformative, silent, compact, efficient enough to work anywhere, and potentially cheap enough for everyone. That's worth paying attention to.